Okay, there we go. So we'll record. So I was saying that please remind me, okay, I need to talk about the exam. There were some exam questions that some of you had questions about too. So I want to make sure I address those. So just remind me at the end. Okay, so the CH2 and the CH2 that you're adding, that is the methylene part here. The CH3, you know that as methyl. These are the methyl groups. So if you had a chain and you had another branching happening here, you would call this the methyl group. Similarly, if you had a long chain and you had, you know, something like this would be called ethyl. So what happens is that in the general nomenclature, the CH2 here, this is called methylene. And if you had two of these would be called ethylene. And you are right, if there were three of them, they would be called propylene. Okay, so they end in the ene because of the proportion of the carbon and the hydrogen. Remember, alkenes are CnH2n. So a CH2 is actually CnH2n. And so because of that reason, it's in a methylene and ethylene and propylene kind of a thing. And it's a general name because, yeah, it can get confusing, okay? If somebody doesn't know the rules of the general nomenclature of why it is coming, where it is coming from, then you might think methylene is an alkene, which, you know, methylene cannot be an alkene. There is no alkene with one carbon, okay, in there. But ethylene can be confusing because, yeah, you can have ethene where you have two carbons, okay? And so understand that if you have a lean thing, then that is two hydrogens, okay, with one carbon, or in this case, ethylene. So when we come to that nomenclature, I'll mention that to you, okay, in just a minute. So that's the whole concept behind the methylene and the ethylene and propylene, okay? So here, let me give you another example. Maybe that will help out then. So right here, this could be called ethylene dichloride. Because here you have two chlorines. The problem with this nomenclature is that you don't know where the chlorines are, okay? Because this could also be ethylene chloride, although it can't be ethylene chloride because this is CH3 and this is CH over here. So this is not an ethylene group. This is an ethylene group, okay? But I don't want you to get carried away in the nomenclature for ethylene and propylene and all that. The methylene chloride is the most common one that you will find, okay? So don't name this ethylene chloride. Just stick to the normal nomenclature, which is 1,2-dichloroethane. Okay, that would be the IUPAC nomenclature. But methylene chloride is an extremely common name, okay? Then let's talk about another common one, and that is CHCl3. CH3L3 would be trichloromethane, but the general name for this is chloroform. So chloroform doesn't really tell you how many carbons you have. I mean, at least methylene chloride was telling you how many carbons you had, but chloroform doesn't even tell you that. Okay, so it's a little bit of an issue, but once you know what you're dealing with, it's not an issue, okay, at any point then. So in any case, once you start having more than one halogen in there, then you have to start indicating where that halogen is. So 2,2-dichloro butane in this case. So whatever it is, okay? And remember that if you have something like this, like chlorine and a methyl group, you will start from chlorine only because chlorine is alphabetically superior, okay? So not because of anything else. Even if you did the numbering the other way, 1, 2, you will still have the lower numbers, but by doing it 1, as in with chlorine, it gives you both the advantage of having a lower number as well as alphabetical, okay? So try to keep that possible if it is, okay, to give the lower number and keep it alphabetical. That would be a problem more for cyclic, not for straight chain, okay? Just a little bit back here again with the chloroform. So if you had chloroform, that would be with the chlorine. If you had bromine, this would be called bromoform. CHI3 would be iodoform. Okay, so those are some of the common names that go with these small, very small haloalkanes. Okay, so there are haloalkanes or alkyl halides. Okay, whichever. This is, of course, the general. This is the IUPAC. Okay, so when you're ending with an ane, that's an IUPAC name. Did you have any issues with the nomenclature? Was there any point where you thought, I don't get this? No. Okay. Please don't forget at this point in life, you are going to be expected to know the R and S. Okay, it's automatic that you're going to have that. So make sure that you don't forget any of your stereochemistry. So here we haven't said anything, although I think I already gave you a chlorine compound back when we were doing stereochemistry. So you already know the nomenclature of that. But what I'm saying is don't forget your stereochemistry. Okay, that's still important. The other thing I want to remind you of before I move on from here is your primary, secondary, and tertiary. Okay, so if you remember, we've talked about this. So this is a primary halide because the carbon it is connected to one carbon. This is a secondary halide because the carbon it's connected to two carbons. And then here is the tertiary halide in which the carbon that the chlorine is connected to three carbons. You can't have a quaternary one. Okay, so primary, secondary, and tertiary halide. This will become really important in this chapter. So we learned the classification back in, I don't know, chapter 2, I think that's where we did it. Okay, so that is the classification of haloalkanes. And I think I have you do that in your PowerPoint study also. Maybe I did. Yeah, I think I did. Okay, identify them as primary, secondary, and tertiary. Some of these names are killer names. Okay, I know. So all I can say is do your best. Okay, as you can. And some of this nomenclature, I don't know if I'll go on it specifically, but that was the one that you also had little trouble in your exam. So I will go over it at the end, okay, of the class. So you can see if that you got that correct or not. Okay. So one thing I want to talk about before I actually get into the reactions and whatnot is the physical properties of these molecules or of this whole class. We generally start with point. So here,
it's breaking up again.
No, you can't handle this. Okay, sometimes again, I'm just trying to mute and unmute and see if it works. How is this? Is it better again?
Yeah, working again.
Yeah, okay, all right. Well, let me know. Yeah, don't hesitate. Okay, let me know and then I will log out and log in again if that happens. Okay, so let me see the attendance also. Oh my God, I think there are some people missing today. Okay, we'll take that at the end also. Okay, so melting point and boiling point. So you can hear me. If you compare the boiling points of alkanes with alkyl halides, which one should be higher?
Alkanes.
Alkanes. Was that Misha?
No, Shamar.
Shamar. Okay, Misha has yet to answer a question for me in class. Are you there, Misha? Okay, so think again, Shamar. Alkanes or alkyl halides? You have to think in terms of what determines a higher boiling point. Oh, let's go back into thinking about physical.
Just electronegativity.
Electronegativity. And so what exactly are we looking for in there? So electronegativity leads to what?
A higher boiling point.
Higher boiling point. There is some step you skipped in the middle, Alexander. One little step.
Polarity.
Polarity, that's the word. Okay, so polarity is important there because the more polar the molecule is, that is what determines the intermolecular forces. Okay, so if you're looking at something like CH4 versus CHCl3 or CH3Cl, what are the intermolecular forces we are talking about? So in CH4, what molecular forces do we have, and what do we have in CL? So let me ask, Luna is not here, I think, so we'll go to Jessica. Jessica Cosito.
I couldn't hear that question because it was breaking up, so I only heard like.
Oh, what is the intermolecular force?
For which one? For
Whichever
what?
one. Whichever one.
Whichever one from what? I don't know.
What are the intermolecular forces here in CH4?
Hydrogen?
No. What about CHCl3 or CH3Cl? Okay. Alia, do you want to help Jessica out?
In CH3Cl, it's dipole in London.
Okay.
And then CH4 is just London.
Just London forces. That's true. So in this one, the CH3Cl, the primary force would be dipole-dipole. And remember, we are sticking to just one major force, okay, that we talk about. So dipole-dipole forces have increased because of the polarity. So when you have more dipole-dipole, then of course the boiling points are higher. So when you want it higher, you want it and alkanes. I have a feeling I'm going to get stuck out somewhere. Is my voice still breaking?
Yes.
Occasionally.
Okay.
It breaks periodically, yeah.
Okay, not all the time. I don't know how it's going to record because maybe if it's recording and maybe you can catch up on that one, I don't know. Okay, we'll see. Solubility in water. So Adelio, if you're here, what do you say? Yes or no? Adelio, not here. Okay.
His internet is out right now.
His what? His
Internet is out right now.
Oh, goodness. Okay. So, Christopher, solubility in water, yes or no? What do you think?
For CH3Cl?
Sure, yeah. Alkyl halides, because we're not talking about alkanes, so alkyl halides. Just take that one.
I'd say they'd be soluble.
You think it will be soluble? So, if you're trying to dissolve something in water, what is the intermolecular force you need to dissolve something in water? So, what is the intermolecular
London
force?
dispersion.
What is the intermolecular force in water? The main intermolecular force.
Hydrogen bond.
Hydrogen bonding. I was hoping for Christopher to reply. So, but yeah, it's hydrogen bonding. And so does CH3Cl have hydrogen bonding? It does not have hydrogen bonding. So which means they're actually not going to be soluble. Okay, so alkyl halides are not soluble in water because their intermolecular forces don't match up. All the physical properties have to do with intermolecular forces. It's one of those fundamental things, okay? So if you need a review on intermolecular forces, chapter 1, okay? Back again, but we can't keep going back, okay? So please make sure you keep up. So then number 3, no solubility, then we have to talk about water. So which means is it heavier than water? And Robel, this is a question for you.
The density of CH3Cl is larger because of the molecular weight.
Very good. So higher. Okay, very good. Good logic there also, because yeah, it has to do with the molecular weight. Okay, so dichloromethane, if you noticed the video that I sent to you for the steam distillation, hopefully you noticed that the dichloromethane was the bottom layer. Okay, in everything, in all the extractions we were doing. The extractions you did with toluene when you were in the lab for benzoic acid, the toluene was the upper layer. Okay, but now dichloromethane is the bottom layer, which is why we write out densities of substances so that we know where we're going to find them. Okay, so those three are the main thing. The fourth one, which is always the hard one to do for us, because unless you're in the lab, how would you know? And I remember mentioning to you about toluene is that you have to smell the chemicals. You don't have to get addicted to them, but you have to smell the chemicals in order to identify the chemicals in case you had to. And the odor for all of these halogenated alkanes is actually sweet, okay? And it is so sweet and is so pleasant that people actually get addicted to this, okay? So just like I mentioned to you about toluene before in the lab, that people get substance abuse because of toluene, you know, it's really one of those kind of chemicals. Dichloromethane is also one of those kind of chemicals, okay, that people can get addicted to. But I will tell you though, when I was doing my work, whether it was research or anything else, for 6-7 years, and even during our teaching labs, I mean, we work with dichloromethane all the time, okay? And I will assure you that I'm perfectly healthy and I'm not addicted to anything, which means that just because you're working with something doesn't mean that you become addicted to it, okay? And so the odor is sweet and it is highly addictive compound, but you have to be careful as working in all these places with all of these chemicals that you keep yourself safe. The other thing about some of these chlorinated alkanes is that they're very potent carcinogens. Okay, and again, I'm telling you I'm safe just because to let you know that if you work safely in the lab, you will not get that much exposure, which is why we always stress on all the safety issues in the lab so that you don't get exposed to chemicals, because it's not just about you getting addicted or me getting addicted, it's also about our well-being. Okay, so all of these compounds are very potent carcinogens, and we have to be careful from them. Okay, so those are some of the physical properties or the properties of halogenated alkanes. Any questions? Okay, so the practical aspects, okay, for all of these. So I'm going to come out of this because I don't need to write anything, because this is just for your general knowledge. All right. Okay, maybe it's going to work now a little bit better than before. But I want to tell you a little bit about these halogenated compounds and where you find them. Okay, so first of all, you find them as solvents. Okay, they're very extremely good solvents. So dichloromethane, chloroform, we use all of these solvents in our lab all the time for extractions, because they dissolve all these organic compounds really very well. Okay, so they're very commonly used as solvents, but again, as I said, one has to be really careful with all these compounds, okay, that we don't get sick, okay, from using all of these compounds. So that's one of the most common places where you find halogenated compounds. And since they're all liquids, okay, since they're all liquids because of their higher molecular weight, it's easy to work with them. Okay, so that's why also they're very common. The second place where you find halogenated compounds is going to be in a lot of the pesticide or pesticide chemicals or killers, whatever you want to call them, but pesticides and insecticides and all those kind of chemicals that we have to kill. And it's telling you a little bit about dichloromethane also. I just mentioned to you that it's a very potent carcinogen, and then I'm going straight to pesticides from there. So you're trying to kill something there also. But a lot of these halogenated compounds are found in pesticides and all, okay? So if you look up any of the structure of pesticides, you will see a lot of chlorines there. You don't find fluorine so much, okay, in a lot of compounds, because fluorine compounds are very hard to work with. So you don't find them as much, but you find chlorine and bromine a lot. Again, iodine is also very different. Fluorine is on the top, most electronegative element, very reactive element. Iodine is at the bottom, very big element and very unreactive. Okay, and so people don't like working with extremes. Okay, so we like to be in the middle somewhere. So chlorine and bromine are going to be the most common halogens that we work with. And generally, if we are working with fluorine and iodine, like I generally tend to mention, okay? Otherwise, it's kind of taken for granted that you're just working with chlorine and bromine and that's it, okay? So all the pesticides that I just mentioned, so, you know, you can find chlorine in there. You may find fluorine, but not that much, and no iodine, okay? None of that in there. So that's another place where you find them. The other place where you find halogenated compounds is in the coolants, okay? And with coolants, we mean like AC, for example, or your refrigerator. The spray containers that we have, okay, so like hairspray or something like that, that will have coolant in it, because all the sprays that we have or the cooling agents we have, those are all gases and they need to be cooled down so they don't all evaporate. So the coolants have to be there. So you might have heard of CFCs, which are chlorofluorocarbons. So that's where we have the fluorine. So CFCs were used a lot in the 60s and 70s when the whole refrigeration and AC business was coming into play. So a lot of CFCs were used, and US was actually one of the biggest emitter of CFCs. It was such a big emitter of CFCs that it actually destroyed the ozone layer all by itself, okay? And so then after that, there was a Montreal protocol that was set, and it was, you know, a kind of a pact between a lot of the countries that we're not going to use CFCs. So a lot of the developed countries don't use CFCs anymore. So there are other coolants which are now called HFCs, which is hydrofluorocarbons. They're not that better, but CFCs used to reach the stratosphere, which is where the ozone layer is, and then destroy them. But the HFCs don't go that high. It doesn't mean they're not in the atmosphere. They are still there in the atmosphere. It's just that they're not as damaging as the CFCs. And tell me who in Florida would want to live in Florida without the AC, okay? And that's why I think Florida was probably one of the last states to be occupied so much, because there was no AC here, okay? And it's very tough to even live one day, unless it's December or January, you know, to live without AC. So CFCs, chlorofluorocarbons, are another kind of very common hydrocarbons that are used. And then there's also the chloroform, and I do want to talk about chloroform a little bit, because chloroform is a very different kind of a small molecule, okay? So it's a tiny molecule, CHCl3, but chloroform was first used, it was almost one of the first chemicals, I think even before some other ones that were used. It was one of the first chemicals to be used as an anesthetic, okay? And again, reading about the history of anesthetics is really interesting, because how did people do surgeries before? Okay, before anesthesia was around, how did you do surgeries? How would you pull a tooth out? Okay, and actually, if you look at anesthetics, there are a lot of different kinds of anesthetics out there. So the common anesthetic would be the one that you inhale. Okay, so completely you're out, okay, for whatever time there is. And the anesthetic agent, the doctor, the anesthesiologist, is usually God, because he's going to put you under and he's going to pull you out of it, okay? And so he is the most highly paid doctor of all, okay? So anesthesiologists will deal with that, okay, where you have the gases going in. Those are also halogenated compounds, okay? So they put them in gas forms. The smaller molecular weight ones, now chloroform, for example, or CH2Cl2, these are heavyweight, okay, because they have chlorine in them. But if you have fluorine in them, fluorine is much lighter. And so those agents are used more as anesthetic agents. And so you have that one, which is inhaled. And then you also have ones that are injected. So those are the IV, okay? So if you inject anesthetics into the body. And then the last kind of anesthetic agent is the topical one, which you kind of just rub on the skin and it'll just be a topical thing, okay? And it doesn't last that long either, okay? So there are three different kinds, and all three of them are very different in their composition, okay? So the ones that I'm talking about are the ones that put you out totally. And it's so chloroform was the first one to be used as a complete anesthetic agent. but people stopped using it because it turns out it's toxic. Okay, and when you read about the history of all of these things, it's just so interesting, and it is amazing. It's amazing what scientists will go through to figure something out. I mean, they will literally disease themselves. They will make themselves sick in order to study something, you know. So a lot of this, you know, the people who are studying medicine, they would do things to themselves that I can't even imagine, okay, of doing. So it's almost to the point of torture. But in any case, it's, you know, I shouldn't say thanks to them, we have all of this, but really, thanks to them. You know, we have a lot of new agents which are a lot better now, because chloroform, as I said, is a carcinogen, you know, so it's much better to use something safer. Chloroform is still the choice of compound when you want to kidnap somebody. Again, didn't say that, all right? I know it's recording. So you would take like a, you know, a piece of cloth or something and douse some chloroform on it, and you know, that's it, and we are done. Okay, and so don't do it. Okay, don't ever do it. But of course, you don't even know where to find chloroform, so that's a good thing. Okay, but in any case, so these are some of the more common functions, okay, of all of this. Now we have version etomidate. What is etomidate, Christopher? What's etomidate? Christopher, are you there?
Oh, Etomidate's an anesthetic.
Oh,
Same
it
with
is?
Versed.
Okay.
We also use propofol as well. So thank goodness we're no longer using the other ones.
Yeah, that's true, but it still depends on what kind it is, you know, so I don't know which kind this one is. Of course, there's so many. So is this like a topical or an injection one? What kind is it, you know?
These are all IV given. Versed is a what's the word? It's a benzodiazepine.
Okay, so that's definitely not chlorine in there, okay, because right, the benz tells you it's a benzene thing. So yeah, the ones that are injected into you or the topical I was just
It's
like,
hard.
exactly.
It's hard to hear what you're saying.
Again. Okay, all right. So those are some of the functions of was that we had still breaking up. Oh my gosh, this is so much fun today because my laptop is getting pretty hot right now. I think what I need for it is
We're still having trouble hearing you.
okay. Not getting better,
No,
is
it's
it?
not getting better.
It's not getting better today. Okay, so let me see who's going to become the host now. This time it's going to be Alia. Are you ready, Alia?
Yes, I'm sorry.
Okay, all right. So you're ready for